Okay, Le Chatelier's principle is the end of chapter 13. Le Chatelier's principle tells us if a system is at equilibrium and it's disturbed by a change in temperature, pressure, or concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. So what does that mean in terms of a chemical equation? Well, when it's under stress, it will shift to relieve that stress. And we just said stressors are changes in concentration, changes in temperature, and a change in pressure. Stressors do not include adding an inhibitor, something that would slow down a chemical reaction, or a catalyst. I think you guys don't have the revised note packet, so it looks like there's 2 blanks here. It should really just be 1. The only way to change the value of an equilibrium constant, remember, is to change the temperature. That's something we already learned, but just reminding you. So what happens when we add or remove chemicals in a reaction? Well, you're changing the concentration. So adding chemicals in the reaction, so if I increase, so this is increasing concentration, the reaction will shift away from that side of the reaction. So if I increase the concentration on the left, it's going to shift right. If I increase the concentration on the right, it'll shift left. Removing chemicals in the reaction will shift the reaction, just changes to towards that side of the reaction. So if I decrease something on the left, the reaction will shift left. If I decrease something on the right, it will shift right. What if I add chemicals other than those that are in the reaction? Well, normally adding chemicals that aren't in the reaction will have no effect on the equilibrium. However, there are some occasions when adding a chemical will decrease the concentration of a chemical in the reaction and thus taking that chemical away from the reaction. So sometimes we might add a chemical to a reaction and it has a subsequent reaction with something in the reaction already. So it draws that substance out. So then it acts like you're decreasing something and then it will shift toward the decrease. Temperature shifts. When heat is added to a system, the reaction will shift away from the side where the energy is. So increasing temperature or increasing heat is kind of like increasing concentration because it's going to shift away from the increase. So for an exothermic reaction, meaning the energy value is on the right, if I increase the temperature, the shift of the reaction will go to the left. And for an endothermic reaction in which the temperature is on the left side, if I increase it, will shift the reaction to the right. What about pressure? Now, pressure only affects the system when gases are involved. So when the pressure is increased, the reaction will shift to the side of the reaction with the least number of moles of gas. And when the pressure is decreased, the reaction will shift toward the side of the reaction with the most number of moles of gas. If the moles of gas are equal on both sides, so if moles of gas equal moles of gas in a reaction, then pressure has no effect. adding an inert gas usually has no effect on the equilibrium constant. If we're at a constant volume. Now it also has no effect if it's added to a system at constant pressure. If you increase the pressure and there's a constant volume, then everything will shift and the partial pressures will actually remain the same. If you increase or you add an inert gas and you're at a constant pressure and your volume is changing, then it will also readjust itself. And adding a catalyst will shift the equilibrium to neither side. Catalyst only affects the rate. So it will affect the rate of the forward reaction and the reverse reaction in the same capacity. Okay, let's look at the famous Haber reaction, a change in reactant or product. The Haber reaction is the production of ammonia from nitrogen gas and hydrogen gas. So if I add a reactant or a product, it shifts away from the increase. So if I increase N2, right here, if I increase N2, then my reaction is going to favor the forward reaction and I'll wind up producing more NH3. Just as if I increase NH3, that increases the concentration, it will shift the reaction to the left, favoring the reverse reaction, meaning that we'll start producing more N2 and H2 as the NH3 breaks down in order to reach equilibrium. If I decrease, okay, so say I decrease N2, take it away, then the reaction is going to favor the reverse reaction. The NH3 is going to break down because it's going to try to replace the loss of the N2. And subsequently, if I were to decrease NH3, it would favor the forward reaction because it would want to replace the NH3. As I said, the Haber process is the production of ammonia from the reaction of nitrogen and hydrogen. This is really significant in the use of agriculture, where ammonia-based fertilizers are of the utmost importance for nutrient balance. In this example, if H2 is added to the system, N2 will be consumed. So as H2 increases right here, N2 is going to be consumed. Why? Because H2, as it increases in concentration, is going to collide more with N2, meaning N2 will decrease and the formation of NH3 will increase. So initially I increased H2, but as it collides with the N2, it also decreases and this increases. And this just shows you the apparatus that's used in the Haber process. It pushes the equilibrium to the right by removing the ammonia. So here's the ammonia. And as that's removed, this increases. So you have preheated feed gases. So they go through here. Here's a catalyst, okay? And this pump works to circulate and compress the gases, okay? And the recycled, as the NH3 is produced, the recycled and unused N2 and H2 are recircled through here and go back in and get mixed in with the heated gases, and the process continues. So let's look at what happens when we change in reactant or product. So the unreacted nitrogen and hydrogen gases, I said, are recycled with the new N2 and H2 feed gases. So the equilibrium amount of ammonia is optimized because all of the product is continually being removed and the reactants N2 and H2 are continually being fed into it. The effects of volume and pressure. As the volume is decreased, pressure increases. So Le Chatelier's principle tells us if pressure is increased, the system will shift to counteract that increase. So in our example of N2 plus 3H2 yields NH3, two of them. If I increase the pressure, the system will counteract the increase. So remember the rule about pressure. If we increase pressure, it shifts to the side with the least number of moles. So I've got 4 moles of gas versus 2 moles of gas. So my shift is going to be, as predicted, toward the production of ammonia. Let's look at another example. We have N2O4 gas, and that is changed into 2NO2 gas. Decomposition reaction goes both ways. So the system shifts to remove gases and decrease pressure. If I increase the pressure, it's going to favor the side that has the least number of moles of gas. So it's going to shift to the left. And as I said, in a reaction that has the same number of moles of gas, pressure will have no effect. So this is 2 versus 1. In this, there is a difference. It will shift left. An increase in pressure by decreasing the volume. So if I decrease the volume, I increase the pressure, it's going to shift left. The instant the pressure increases, the system will not be at equilibrium, and the concentration of both gases has increased. When this happens, the system will move to reduce the number of moles of gas. The equilibrium constant is temperature dependent. For an endothermic reaction, okay, meaning heat is on the left, it's being absorbed, delta H is greater than 0. It's positive, and heat can be considered as a reactant. For an exothermic reaction, meaning heat is on the right, we know that delta H is less than 0 because delta H would be negative, and heat can be considered a product. So if we add heat, it favors away from the increase. So if I add heat, it would favor the forward direction, and if my delta H is less than 0, meaning exothermic, and I add heat, it would favor the reverse reaction. So let's look at this example. And this is kind of similar to the lab that we just did on Thursday. Well, first of all, COH26 liquid by itself is going to be a pink color. And the COCl4 is blue. So if I have both of these in a test tube at room temperature, pink and blue make violet. So the two of these mixed in a test tube at room temperature are going to be violet. If I increase the heat, what I'm going to see is that my solution in my test tube is going to turn blue, which tells us that the shift would be to the right, favoring the forward reaction. If I decrease the heat and I put the test tube in a beaker of ice water, I'm going to see that it turns pink, because when I remove heat, it's going to shift toward the decrease, which is to the left, favoring the reverse reaction, which would cause the solution to turn pink. All right, let's do a couple practice problems. In a study of chemistry of glass etching, an inorganic chemist examines the reaction between sand, silicon dioxide, and hydrogen fluoride gas at a temperature above the boiling point of water. So we know this reaction is greater than 100 degrees Celsius. So predict the effect on SiF4. So they want to know what happens to the concentration of SiF4 when H2O is removed. Decrease the concentration of H2O. Then my shift is going to be toward the decrease, so it's going to shift right, which means it favors the forward reaction. And the concentration of SiF4 will increase. B, some liquid water is added. This is an all gas equation because it's above 100 degrees. Remember, this is occurring at above 100 degrees. So as soon as I add liquid water, this H2O liquid is going to get converted to H2O gas because the reaction is above the boiling point of water, which is or therefore going to increase the concentration of H2O gas, which is going to cause a shift to the left, and that favors the reverse reaction, which means that the concentration of SiF4 will decrease. C, HF is removed, so I'm going to decrease HF. Remember, when I decrease, my shift is going to be toward the decrease, so it's going to shift left. So again, my reverse reaction is favored, and my SiF4 is going to decrease. And the last one, some sand is removed. Same thing. If I decrease SiO2, the shift is going to be to the left, and the SiF4 will decrease. Okay, and the last one that's in your book, you should recognize this. So what kind of reaction does this look like? You have a nickel catalyst, and the reaction is at 750 degrees Celsius. This reaction is very exothermic. So what that means is that our heat is being produced. So if H2O is removed, we know it will shift left. And it's going to favor reverse reaction. The temperature is increased, same thing, it's going to shift left. Helium is added. Helium, there's nothing with helium, so this is going to be no effect. CO is removed, so CO is on the right, so it's going to shift right to replace the CO, so it's going to favor the forward reaction. And the volume of the container is tripled. So when I increase volume, I decrease pressure. So a decrease in pressure will shift the reaction to the side with the least number of moles. So I've got 2 moles total, 1 mole of ammonia, 1 mole of water, and over here I have 4 moles total. So when I decrease the pressure, it shifts to the side with the most number of moles. So it's going to shift right. And that will favor the forward reaction. All right, so that's basically Le Chatelier's principle in a nutshell.